the skin resistance on the wall depends on the skin depth. So that would be dependent on the frequency. Because as we said, the skin depth 1 over pi f mu times the conductivity. So you can see here the skin depth here, it depends on the frequency of operation. So it means then the skin resistance also depends on F. So Rs is equal to 1 over conductivity of the wall times the skin depth. So for you to get the attenuation constant due to the wall, then you need this skin resistance and the skin depth to be able to calculate it. And then you get the scaled value of that. Then eta is the intrinsic impedance of the wave, which is normally given as anyone who can remember what is the formula for eta? What is the formula for eta, the intrinsic impedance?
It was the permittivity over the permeability over the permittivity. Mu over.
Yeah. That is 1 power. Now I need to move on. So you have eta is equal to mu over eta, well, over permittivity, which is the epsilon. So that will give you 120 pi, which is 377. But for the dielectric, the attenuation constant is given by that. So probably you may master it by an example. Let me change to the other device. Wow, it's crazy. Are you able to see my screen on this other one?
Yes, yes, you can.
Yes.
My volume is low, eh? Unfortunately, now we are not able to write. I hope you'll be able to follow. So we were somewhere here. Hope it's large enough. All right, so we see so we have the expressions for this. So we want to consider a case here where we have an air-filled rectangular waveguide with the sides which are given. A is equal to 4 and B is equal to 2, which transports energy in the dominant mode at the rate of 2.3 milliwatts. The frequency of operation is 10 gig, and you're supposed to calculate the peak value of the electric field intensity in the waveguide. So we are saying it is working in the dominant mode, and the power is given. So this is the power that is injected. The frequency is at 10, so we need to calculate the peak value of the electric field intensity in the waveguide. All right, so for dominant mode, remember we said A is more than B. For TE10, we can actually calculate the cutoff frequency from this formula. Because it is a 1-0, remember here we are just told it is a dominant mode, so it is upon you now to decide the mode. So it's a TE10. So you have here. So if you're just told dominant mode, you will definitely choose a TE10. What if you're told a dominant TM mode? Which mode will you select? What will be the value for M and N?
It's TM11.
TM11, yes. Okay, so you'll just be told transport energy in the dominant TM mode. So you must know it is TM11. Even from the calculations, you can tell that. So from the field equation, you can calculate the cutoff frequency. Here is stated that it's 3.75. I hope that is correct. And then you calculate eta for TE. So you'd remember also that these equations are derived. So eta for TE, the TE mode, is different from eta for TM mode. The eta for TE mode will always be higher than the TM mode. So you'll note through the tutorial, I will give examples where you were to use the eta TE and eta TM, and you'll realize that eta TM will be less. So the intrinsic impedance for the TE mode, because these waves actually propagated differently with different fields, where we have different half circles, prime, which is 377, divided by that scale, 1 minus FC over F squared. So this one comes to 406.7. I hope that's correct. And TE10 mode, we saw from the equations that EX will be 0. EY, you can just have something on the on the amplitude. So E naught Y sine of pi x over A times E exponent minus J BZ. That's the general equation for wave propagation. Then now to calculate PT, remember we said PT is the sum of EY squared plus EX squared over 2 eta from the pointings vector here. Okay. But for that mode, TE mode, we said EX actually diminishes to 0. So we only have EY squared over 2 eta. It's the simplest you can have. So then it means then we can integrate for the side A and the side B of the waveguide of EY squared over 2 eta dx dy. I don't have a pen to show how that comes, but just try to at home. That PT will now reduce to, using that equation of what is given for EY, you'll have E naught squared over 2 eta. Then you integrate from 0 to B dy, and then 0 to A of sine squared pi x over A dz. That's EY squared. I think that one you can see from the equation of EY, right? That one you can see from here. So if you square that one, it reduces to this. Now the integration, the first integration becomes, that first integration is a dy, so it's just b, isn't it? So we have E naught squared b over 2 eta. Then now we integrate this one, sine squared of pi x over A dz. So you can reduce that, take note, you can rewrite the sine squared, the integral of sine squared x dx. You can rewrite sine squared in terms of cosine, which is 1 minus cosine 2x. So sine squared x is the same as a half of 1 minus cosine 2x, a half of, in bracket, 1 minus cosine of 2x. So with that one, you can then integrate, and you realize it reduces to a half of A. If you integrate it, it reduces to a half of A, this one here. So try to do that at home, make sure you get it. So if it reduces to a half of A by rewriting sine squared x as a half of, bracket, 1 minus cosine 2x, then it means then we'll have E naught squared AB over 4 eta, because that reduces to a half of A. So try to get that at home. So if you have, now the power is equal to 4, is equal to E naught AB over 4 eta. And we were asked to compute the maximum electric field intensity, isn't it? Calculate the peak value of the electric field intensity in the waveguide as we excite it. So when you excite that mode, what is E? So from there, because we have power to be 2 milliwatts, you can actually now, was it 2 or 2.3? 2.3 milliwatt. So then we can now rearrange this equation here, make E naught the subject of the formula, and calculate that E naught from that equation. I hope it's clear. To a given power, we don't know E naught. We have A and B, and we can calculate eta for TE mode. Now we can do the same for TM and see what you get. TM dominant mode, TM11. It's going to be a bit complicated, but not much, because it's just the sum. You will have to sum the integrals. Okay, I wanted us to look at something where now we have a lossy dielectric. Not necessarily lossy dielectric, but in a case where we have a dielectric inside the waveguide. So quickly we can go through this 1 second example. Is there any question on the first example? Also try to see if what the E will compute is 68.39 volts per meter. Okay, so some of this we'll repeat in the tutorial. So example and second one. So a polystyrene filled rectangular waveguide with the sides A and B given 4.2 and 2.6, and the conductivity of the wall is given. This conductivity of the dielectric, this is polystyrene, the one that is filled inside. So that's I should have written sigma D. So it's equal to 10 neg raised to neg 17 Siemens per meter. Delivers a power at the rate of 1.2 kilowatt to an antenna from a transmitting port. Frequency of operation is given as 4.8 gigs. So you're supposed to calculate the peak value of the electric field intensity in the waveguide. The waveguide is excited in T10, so it's the same as the other one. Then we are now supposed to find the power that is dissipated at a point which is only 60 centimeters away from the transmitter. So you can sketch it. So you have a transmitter, then you have a waveguide connected from the transmitter to the antenna. In this case, now we call it transmit antenna. So the transmitter is the processing unit. Then you have the waveguide, and then the antenna connected on the other end. So 60 centimeters away from the transmitter towards the antenna, we want to see the power that is dissipated. So in this case, we have a dielectric inside the waveguide. So the fastest way to check whether this is a lossy waveguide due to that dielectric is to calculate the loss tangent. What is the loss tangent? Is the ratio of conduction current to the displacement current. And remember, the conduction current JC, current density will be JC is equal to rho. It will be equal to sigma times the electric field intensity. So we can write J C is equal to rho, or is equal to sigma times electric field intensity. Then we have the displacement current JD from first principles. You can derive this one. In the third year, I think we did this. So you, for the JD, you have, which is the current density for the displacement current, is given as omega times D, which is the charge density. So you have omega times D, and the D is the same as epsilon times E. Epsilon times E. So if you divide JC, which is sigma, then you'll have the ratio, which is the loss tangent, as sigma over omega epsilon. So we calculate the loss tangent there. You can see that it shows that actually it is much, much, much less than 1. So the contribution of that dielectric to the attenuation will be very minimal. Okay, so you can actually consider this a lossless dielectric medium. So this is classified as a lossless dielectric medium. B, you can calculate the intrinsic impedance. We say that is mu over epsilon, but now we have mu over epsilon naught is 377, which is 120 pi. So it means you divide by root of the relative permittivity. So you get 236.1. We are given relative permittivity as it's given there for the dielectric, which is 2.55. So you can use that to calculate that intrinsic impedance. Velocity in this medium definitely will reduce because of that permittivity in the dielectric. So again, velocity we know is 1 over root mu epsilon. So with that, you can divide by the relative permittivity. What about cutoff frequency? Because it's a T10, the coefficients of n reduce. So we have only 1 for m. So we have C over 2a. You can calculate 2.2. So will there be forward propagation? We look at our frequency of operation is given as 4.8. So the cutoff is 2.3. So this is okay. 2.23 is fine. Then we have the attenuation constant. So now we use the attenuation constant for the conductor and the dielectric, the wall of the waveguide, and also the dielectric inside. So when you do the calculations, you can see that is compared to the wall of the waveguide, this is too low. You could even assume it. So the loss due to conductivity of the waveguide walls is larger than that due to the dielectric medium. Okay. So actually, it's just almost, even if you were to add these two values here, it would still look like just the first one due to the conductor. So it's approximately equal to just to the conductor. And we had declared that dielectric to be lossless due to the loss tangent. So if you are given just the loss tangent, you can actually use it to determine whether it's going to be lossless or not. Now, the skin resistance is given also. Here we are using, you see, is 1 over the conductivity times the skin depth. But because we are not given skin depth, we can calculate it from the general formula. The skin depth is 1 over root of pi f mu times sigma, which is the conductivity. And we have another conductivity here. So you can see then if we put the square root, we'll have pi f mu over sigma c. That will give us the skin resistance, which we need in calculation for the attenuation constant. So you have Tx power Pi at the input, the power loss PL, and the power delivered at the antenna is PA, isn't it? So if there's a loss, then it means the power that is delivered plus the loss is the power that is injected. So Pi is P loss plus P that is delivered at the antenna. But how does the P that is delivered at the antenna change with distance? We know that PA is equal to Pi exponent of minus 2 alpha Z, exponential decay. So it means if we are to derive the power loss up to a point Z within the waveguide, any point Z within the waveguide, and there's a loss. So it means what we are talking about, the loss will be the power injected minus the power that is delivered at the antenna. Okay. So PL is equal to, you can see, rearrange this one. So PI is PL plus PA. So, and PI also has, PA is PI times that exponent here. It means we can say that PL is actually PI minus PA. But PI, from here, you can rewrite it. You can rewrite it as PI is equal to PA times, so PI you divide by this, the right-hand side. So PI is equal to PA exponent of positive 2 alpha Z. So in that case, then PL is equal to PA times exponent 2 alpha Z minus PA. So you can substitute that. So you have that equation. So you can calculate PL, the power loss, because PA is given at the antenna, that is the one that is delivered at the antenna. Let's see. I hope you drew it in a way that you understand. So delivers power at a rate of 1.2 kilowatt at the antenna. So that's the one at the antenna. So that is PA. So you have it there. So when you calculate that, you see that the loss is only, was this kilowatt? This should be kilowatt, not milliwatt. Can you do this calculation and see what you get? This one should be kilowatt, not 10 raised to 3. We are given in kilowatt, isn't it? So can you make that change here? It should be 1.2 times 10 raised to 3, isn't it? For PA, it's in kilowatts. Then 60 centimeters, that's 0.6 meters. All right, so I hope again you just need to master the use of this equation. So here it looks like even if we didn't use this second equation for the dielectric because of the loss tangent, we would just use the first one, be able to compute that. Any question there? I can't hear, so it means it's flowing. Let's have this last one. I wanted us to have a look at this because this will help you with the tutorials that I will give soon, just to see how you deal with such a question on group velocity and phase velocity. So you're given a standard air-filled waveguide, which is fed by a coaxial cable, that's excitation, with a 4 GHz carrier. So you are to investigate if a TM11 or a T1010 will propagate, given the sides of the rectangular waveguide, 8.6 and 4.3. Then you have to determine the phase velocity and the group velocity in each case. So what do you need to do there? You compute the cutoff frequency. For a TE10 is easy. You eliminate the second term, which has N, which you normally have FC is equal to C over 2A. So we find that the cutoff frequency is 1.737 for that waveguide, but your carrier is 4 gig. So you realize that the carrier frequency, the center frequency is higher than the cutoff. So there will be propagation, forward propagation. What about a TM11? Can somebody calculate TM11 and tell us right now? TM11, what is the cutoff frequency? I hope someone is calculating. TM11, what's the cutoff frequency? But yeah, I hope I'm audible. Anyone there?
Yes, could you kindly go back to the, yeah.
Yeah. I thought maybe the internet was cut off. So TM11, or you want to see the formula for the cutoff? You're not used to it yet.
I was looking at the dimensions A and B.
Oh, you want to look at A and B. A and B is 8.6, 4.3. All right. No, not yet. Okay, so you try to calculate the cutoff frequency for TM11. You let us know if you get something like 3.88 gigahertz. Then we look at the phase velocity. So 388 is also below 4 gigahertz, so it will propagate forward. So phase velocity is omega over beta. the phase velocity, we agreed that actually you are looking at the speed of a constant point of the phase of a wave. So you check over 2 pi radians, okay, what is the rate of change over 2 pi radians? So you will have the phase velocity as maybe and 2 pi radians will give you the wavelength. So it's wavelength over the period, which you can say wavelength times the frequency. So if you add the 2 divide by 2 pi, then you realize you have omega over 2 pi over lambda, which will give you omega over beta, because beta is this wave number, which is the same as 2 pi over lambda. So you'll have phase velocity being omega over beta. But it is scaled in this case. So you'll have k being omega times, remember we have k as the square root of omega squared times mu times epsilon. So you can have omega over outside, or you can have it inside this, outside the square root here. Then you have now, so you have omega over omega times root mu times epsilon. And we know 1 over root of mu times epsilon is actually c. So you can have c over that scale, root of 1 minus fc over f squared. So using that, you can see that actually the phase velocity can be higher than the velocity of the wave. So it's 3.33 times 10 raised to 8. What about group velocity? Now group velocity, that the wave is propagating at a speed that is the product of the phase and the group propagates. Okay, so you can have a wave, a carrier, and then you modulate a signal onto the carrier. So then it becomes an envelope. So the speed at which the envelope travels, modulated envelope travels, is the one that is the group velocity. But the carrier itself now is like the phase velocity. So you'll have the speed of travel being the phase velocity times the group velocity. So it means if we know c, we can calculate the phase velocity if we know the group velocity, or we can calculate the group velocity from the phase and the speed. So we'll have 3 times 10 raised to 8 squared over Vp, which should give us the Vg. So Vg will be 2.7, which is lower than the speed of the wave and also lower than the phase velocity. So you can consider, if you want to know exactly what it is, so consider carrier, which you need another wave that you modulate onto it. Okay. So that will give, then you look at the phase of that carrier. How is it changing? So it will be faster than the speed of the carrier. And then you look at the group, which is now the envelope that is having a signal which is modulated onto it. What is the speed of it? So you have 2 signals together. So the speed is going to be lower. So you have 2.7 times 10 raised to 8 meters per second. So you can see it's slower than the carrier itself. And the phase of the carrier is changing at that rate. And this is when it is in TE10. So you can also calculate in TM11, what would be the phase velocity and what would be the group velocity. Looking at the equation for the cutoff frequency for TM11 and TE, now that you know that the cutoff frequency for TM11 is higher than cutoff frequency for TE10. What do you think about the phase velocity for TM11? Is it going to be higher than TE10 mode or less? Maybe it's not easy for you to determine by this point until we do another example, but it's fine. So the phase velocity we can see here is phase is frequency dependent. Okay. So you need to calculate the phase velocity for Tm 11. Check if you will get 12.5. I'm not sure. 12.5 times 10 raised to 8 meters per second. And then the group as 7.2 times 10 raised to 7. 7.2 times 10 raised much lower. So that with that calculation, for you to get that value, so that we finish this revision on waveguides and the resonator. Then after that, we start your lectures. So class rep, did you agree? Sorry, the time is past. Class rep, did you agree on the groups?
Not yet, but I will send them to you by the end of the week.
Yeah, you just try to discuss. You know, that is also teamwork. You need to evaluate whether you are able to divide yourselves into groups and be able to effectively form teams. Okay, right. So if there's no question, you can submit your attendance on the chat. Next time, either we'll do more examples, I'll see, or we move on to EM resonators immediately, because I don't think this was supposed to be revisions. It means you had met them before. We won't waste time. Yeah. So the resonator is just now we block the end. You know, these were hollow structures, so we'll block the end of those hollow structures so that we form a cuboid or a cube and see how the standing waves now form within there and the energy that is contained. Using the same, you could have a dielectric in them there or air.